Hello everyone, could you hear me?
Yep, we can hear you.
Yep, you did.
Okay, thank you. I haven't posted the last week's video yet. But don't worry, we will pick up where we were, and then I will deliver the video as soon as I can. Let's first review what we talked about last time. Oh, before I start, do you have any questions like lab submission, things like that?
I did have a question about the lab submission. I know it's due tomorrow.
Yep.
For the Canvas submission, did you just want like a text file or like a PDF? Like how did you want us to submit it on Canvas? Like the format of it?
Oh, so you just submitted the bits.c.
So a Word document.
You don't have to submit document. You just following the handout PDF. You just need to submit the bits.c. And
Okay.
yeah, and if you have the team members or you work alone, the bits.c at the very beginning of the file, there's a place you can put down your username, ID, the information over there, so that our TA could recognize this is your work. That's it.
Okay. I guess, is there a way to download the bit.c? I was looking in the instructions and didn't see anything, so I kind of just copy and pasted everything into a text file. Is there like a SCP command that we can do to like download it onto our desktop from Blanca?
Yeah, let me write down. There's a command, secure copy. We can copy the stuff from Blanca to your local computer, and then you upload the .bits.c. That should be fine. Let's see. Your username. I'm typing it. SCP Blanca ECW path to your file. Okay, I typed the command you can use. This again use a secure copy. The first parameter is where the bits.c come from Blanca, and you specify the path. And then second parameter, I just put dot. That means copy to your current folder or for your local computer. And then you can copy bits.c from Blanca to your local computer. Yeah. Any other questions? Okay, let's get started. Let's review what we talked about last time. Last time we talked about the control flow. That's the place we want to branch in. We look at how the assembly implement the branching. There's three elements make this branching possible. The first one is the arithmetic operations, or CMP or test, which could set up the second element, which is the conditional code. And then we have a third element. Usually it's a conditional jump, checking the conditional codes either to make the jump or not. So we can branch based on the conditions. We talk about jump instruction. We try to initialize the program counter. And the address it is having is the address of the instruction the computer is gonna execute. And when we do a jump, we changing the value of the program counter or RIP, register RIP, so that we can change where we're gonna execute the program. And then we talk about there's a unconditional jump, JNP, or you can do conditional ones, starting with J, followed by the conditions. We can specify the target address by 3 ways. One, we could give a label for it. The second way, we can put the target address inside of the register, or we can put the target address in the memory. We also talk about how to encoding in the machine level. When we really translate the assembly to the machine level, there's a possibility that this machine level code could be moved somewhere in the memory. Every time we execute the same piece of program, we could start from very different addresses. And if we put down the target address in absolute way, that means if we move the program, there will be a problem. We would jump to the wrong location. So we do it in relative way. We find the baseline address, which is the address of next instruction. And then we have the offset. This is where the relative part comes into play. We calculate the target address on the fly, which is the baseline plus the offset of the fly on the fly, so that we can move our program everywhere without modifying the target address. That's an advantage of doing so. We also talk about the skeleton usually adopts by the assembly how to do a conditional jump. So really, we start with the green block. We look at check the conditions. If the condition is satisfied, then we jump to L2 block. Otherwise, we stay and execute L1 block so that we can execute different blocks based on the conditions. And we talk about how to do the reverse engineering, basically just read through the assemblies, figure out how we put down the conditions correctly in order to make our assembly consistent with the C program. And also we talk about looping. Looping, the difference is we jump back so that we can repeatedly execute the same piece of programs again and again. That's a sign of looping. We jump back. Branching, we usually jump forward. When we jump back, there's many styles we can put down the looping. We have the do while, and here's an assembly code would look like. And the checking part, whether we continue the loop or not, is the green part. It happens in the later part of the do while loop. Or we can have the for loop. You can see the for loop, the testing at the beginning. Yeah, it's at the beginning of this looping, the purple one. We're trying to check whether the condition is satisfied at the very beginning. So different places to place the conditional check, but yeah, it works the similar way. We either jump back or we jump out of this loop. We also talk about this example. We're trying to reverse engineer it. Switch statement is when we have many cases we want to check about. It's much more efficient than writing about a lot of if, else, if, else, if, else, if, else. It's much more efficient that way. The reason for the efficiency is because of the introduction of jump table. For the switch, we have this jump table. It's a table stored in our memory, and usually we have the L7 to denote the starting address of it. We have the L7, so when we plus 0, that means the first entry. If we plus 8, we look at the second entry, and each entry is a target address we can jump to. And we talk about the core part of the switch assembly is the jump. usually it's an unconditional jump. We have the star because our target address is in the memory. So we, following the format, we should put a star. And then we have the L7, which is telling us where this jump table is. We have nothing for the first parameter. Second one, usually we have the index variable stored in one register, and we put down scalar. Let's assume 64-bit machine. This is really the core part of the assembly. And so we mentioned the target address in the memory, particularly in this jump table. So we find the ADDR, the address of this memory. If we calculate in the standard way, it's L7 plus EAX times 8. And the EAX is index. So you can see here, if EAX is 0, we pick up the first entry. EAX is 1, we pick up the second one. EAX is 2, we pick up the third entry, so that we can find the relevant target address we want to jump to. So in this example, if EAX is 0, we jump to L1, right? This is EAX equals 0. If we talk about EAX equals to 1, then we jump to L2. This is where we jump to, so on and so on. So you can see here, the target address is in memory, organized by a table, and the start address of the table is .L7. It could be other levels, but we really have level for that. And then the core piece of the perp assembly is like something like this. So based on the value of EAX, we offset within the jump table to select the right target to jump to. So that's part of the switch. And also we talked about the conditional set. We either set the byte to be 1 or 0 based on whether the condition has been satisfied or not. If satisfied, we set to be 1, otherwise set to be 0. And this conditional set just do this job. Give an example for the conditional set. We also talked about the conditional move. Last time we talked about why we need this conditional move, because it can introduce much performance benefits. When we do some C program, we usually have if a condition, then A equals to 10, otherwise A equals to 20. So based on the conditions, we set up different value for A. So this is quite a typical pattern we use the branching statement, used quite a lot. We talk about our program, our modern CPU is highly pipelined. It is not only reading and dealing with the current instructions, but also it reads ahead the following instructions as well. As a result, it doesn't like something uncertain. For example, branching. Should we take the path, this path, or should we take another path? We don't know. So the CPU usually just make a guess and then try to fetch the instructions beforehand. But if the prediction is wrong, apparently it has take much effort to correct the error. So in one sentence, the CPU doesn't like uncertainty in program, especially whether we should make the jump or not, things like that. It's just risky for the performance. What we can do is use CMove. This is the way we modify the traditional branching assembly to CMove version. Basically, we set up the value inside of the target, and then based on the condition, if the condition is satisfied, then we move the value to the place. Otherwise, we don't move the value. So by this way, we no longer have the uncertainty in it, and our CPU could execute this program smoothly without making the wrong guess. That's why we have this CMove. Okay, this is about control flow. Let me find another one. Okay, now let's look at procedure. Oh, so first off, did we talk about procedure in our previous class? Did we talk about this? Okay, I see. Thank you, Devin and Javier. Thank you for clarifying on that. Okay, let's talk procedure call. You may find the pattern we talk about C program and the way we talk about assembly. For the C program, we have the arithmetic operations. We have branching, control flow. We have variables. We have many things in C program. And the last part we talk about when C have the if else the branching and the looping. We actually find the assembly code have the corresponding functionality to make that happen. That's why we can do that in C. Similarly, in the C program, we have the procedure call. We have the caller function, makes a function call, and then execute the codes of the calling. This process is called a procedure call. And here is quite a simple example. We have main function, we make a function called func, and it gives the input A to the function. And then the func itself is just trying to add 10 to the input and return the value. For this C program, we make function calls. And you may make a guess that in the assembly, we should also have the corresponding functionality in assembly to make that happen. Otherwise, there's no way our C program could do that. The answer is yes. We have the function call as well in the assembly. So here's when we look at assembly code of the C program, we may find here here is func int. This is the label for the callee codes. So you can imagine these two pieces of codes belonging to main and the func. These two codes resides in the memory altogether. So they are at different locations. We need some way to see where they are. So for the callee, we have the func, have the parentheses integer int to be the representative label for the callee program, and also for the main function we just use main. Okay, and for this label, there's many different styles to do that. This is what my compiler gives me. They name the labels in such a way. It could be others. And if you look at the caller, here's something called a function call, call. And for this call, you can make a guess. We're trying to make a function call, right? And we have the func int to be the target address. So here is still a label, even though we have parentheses and it looks like a function name, but in a sense, it's still a label. We make the function call, we actually jump to here. Make the function call, we jump to the callee and start to execute the codes of the callee one by one. Okay, here's what it usually looks like when we make a function call in assembly. We have the call instruction. We also have the target address. That is also a label. That's where we jump to execute the program. And when we finish the callee function, let's see, we want to do the callee function, and you can see at last we have RET. This is the return. This is just telling the computer the callee has been finished. Callee wants to return back to the caller. And you can make a guess. The next after return, the next instruction we're gonna do should be this move L. That should happen after the function call, right? And we tell a story like that, but if we look into it, there's more contents to look at. That is how to jump back. That's the first question. Let's say the callee finds this return, or callee wants to return back to the caller. But right now the CPU is controlled by this callee, and the callee needs to find what should be the return address so that it can set up the RIP, right? The rest in peace register or instruction pointer, right? It has to put the return address. This is for callee. It should put this return address inside of this RIP so that it can return back to the caller. So right now, caller just have no control over the CPU. Callee have the control because the CPU is executing callee's stuff. That's callee's way to make an impact. In the first question, callee needs to know the return address, but a callee may not know, right? Execute the callee's function, but may not know what should be the return address. So callee needs to answer the first question: how to jump back, or where should a callee jump back to? That's the first question. The second question is how to pass parameters. In our example, we have A. We want to pass this A to the function, and the function to the class 10 to make a return. And how this A could be passed to the callee. Like when callee do the program like this, callee needs to know what is the value for P1. Okay, and then it can do something that try to modify P1 by adding 10, right? So callee needs to know P1 at first. But that's not that straightforward. How callee can find out what is the input? That's another question. You may realize that it's only questions for callee. Why is that? Because caller knows the exact answer for both questions. Does caller know where to jump back? Yes, caller can find, oh, here's the instruction I'm gonna execute after the function call. So the instruction after call should be its address should be the return address. So here's the return address. caller know this. Caller know after function call, what should be the address of the instruction it cannot execute. Return address is right here. Caller knows the answer. No problem. Does caller know the second answer? Yes, it is. Let's look at integer a equal to 0. So the caller, you can see caller right here, it's just moving 0 to a place. You can imagine this is trying to set up the value for a. So the caller knows a equals to 1 or no, a equals to 0. It knows this answer, a equals to 0. And the caller knows the second answer. Let's see. Caller knows the second answer. It seems like the caller has to find a way to let Kali know the answers as well. Otherwise, Kali could have some problems. And this is apparently a communication issue. When we talk about communication issue, the quick solution is we need to have a common place to share knowledge, to share the communications. Right? We need a medium. We need a medium to do that. This medium we call stack. Stack, so first of all, it's in our memory or in our RAM. It's a physical existence. You may heard of the stack for your algorithm class. And that stack in the algorithm class is the data structure. The data structure looks like this. This is, let's see, the laundry basket. So at the beginning, we put this pink color clothes into the laundry basket. The next, this process is called push. You push an item into your basket. This is mallet. You can think about this basket to be an array, or array. That is possible. And next time you put another clothes or data item into the basket, the blue one. And the last time, let's see, in our example, we put in the red color. This process is called push. And another process is called pop. Pop is trying to get an item out of it. For the pop, the very first one you get is red. This is the last item you put in, just like your laundry basket. The first item you get is red. The second item is blue. The last one is pink. So that's the order. So the stack is built orders. Last in, first out. So the red clothes, this is the last in, and when we pop, this is the first out. So this is the data structure for stack. And for stack in our class, it is more than data structure stack. So first of all, we implement the whole stack, the physical existence stack, using the data structure stack. That's where the name comes from. But we have the physical existence. It is existing in our memory. And for this stack, the purpose of it is to have the communications between caller and the caller. We just want to have this communication so that caller can tell the colleague the answers for the previous two questions. Okay? So the colleague, if colleague knows these answers, it can solve its issue. And this is what a stack is. And if you look closely at a stack, the return address, this is a place to put down. It should be provided by the caller, for sure, about the return address. And also here you can see we also provide the input parameters on the stack by the caller, so that when callee wants to use these two pieces of information, it can come to the stack to look up the needed information as a result. So the stack is setting up a median between caller and callee to have a way caller can tell what is return address or what is input value. Give these two informations to callee so that a callee function will do its job. This is a stack. Before I continue, is there any questions so far? Yeah, we just trying to motivate why we need this stack. It's a setup way caller can tell callee the return address, the input variables. These two pieces of information. Yeah, feel free to stop me if you have questions. Okay, let's just take a look and how this function call works out. Let's see. Here's a sampling program we're trying to look at. This is the sampling, and then right now we're trying to execute 400563 this instruction, and the instruction is call. Right? We are about to make function call, and let's see what is set up in our CPU. We have the RIP instruction pointer to be the number 400563. Yeah, we are about to execute this function call, right? RIP always gives the address of the instructions we're gonna execute. So that's the computer's way to figure out which instructions to execute in the oceans of assembly. And then also for the stack pointer, we call this stack pointer. It gives us where the stack is. We also use a pointer, right? It's in the memory. In the memory, we should have an address, and when we keep this address, in a sense, it's a pointer, right? This is the stack pointer. It has a lot of FE840. Let's say it's right now pointing to here. This is the top of the stack. And RSP is a pointer. We can find where the stack is right now, or the top of it, where it is right now. Stack pointer. And now we need to execute the program. But right now we're still in the control of caller. So I would say this is caller. Here is callee. We try to execute the function call right now, and you can see what would happen right after this function call is we put the return address on the stack. This is the caller. Oh, callee needs this information. I need to put this information on the stack so that the callee can check the value. So this is the first piece of information we want callee to know. That is address. Any questions? Okay. Check the chat window. And then now we see the very first thing happen is when we make this function call, back of the stage, we put the return address on the stack. We talk about the return address is the address of next instruction after the call. So the return address in our case is 400568. This is the return address. We put this address on the stack. And because we put the address on the stack, we have to move our stack pointer by one place. For the stack pointer, it always points to the top of the stack. Because we push something on the top of the stack, we need to move the pointer to reflect that. And for stack pointer, because our stack just have this weird order upside down, this order. So if we want to have more stuff in the stack, we need to move the stack pointer by subtracting a number. Because the address in our machine, 64-bit machine, that is 8 bytes. So we need to subtract 8. This is the original value. We need to subtract 8 from this value in order to expand our stack. So we have 838 would be the new pointers. Okay, it will be our new pointers. Now the top of stack is right here. We finished the setup for the function call. Oh, by the way, RIP, the instruction pointer, we also need to update that to be the target address, 400540. This is the target address we jump to. This is also the starting address of the callee. So we put the 400540 inside of RIP so that the next instruction we're gonna execute is 400540, which is the very first instruction of call. This finished the first half of function call. When we make the function call, what happens at the back of the stage? To summarize, we first needs to push the return address on the stack. This is the first step. The side outcome is we need to update the stack pointer. The second step is we need to initialize the RIP instruction pointer to be the target address so that the next cycle we could execute the first instruction belonging to callee. We finished the first half of the function call. Is there any questions? Okay, let's continue. We finished the first part of this function call. And then we execute the callee one by one, right? One by one. Let's see, finally we finished callee and hit this return part. And again, let's check about the instruction pointer. It is having 54B inside of it. So our green arrow right now is trying to execute this RETQ, return instruction. For RSP, we still points to the top of the stack. And if you look at the stack, the 568 is the return address. Okay, so the callee knows what should be the return address by looking at the stack. Now we are about to do the return. When we do return, there are several things to have. First of all, the callee would move this return address to RIP. Right? This should happen. We need to jump back to the caller function. How we jump back? We need to change the value for the RIP. What should be the return value, return address we're gonna use? So the callee look at the stack and find the return address. Initialize the RIP instruction point. The second step is we need to delete this return address. It's no longer useful for us. After we return caller get the control, then this piece of return address information is no longer important. So we need to delete that. How we delete it, you can see what has been changed. We just +8 for the S stack pointer. By +8, we literally moving the pointer in a shrink the stack by 8 bytes. In a sense, it is as if the return address is no longer existing anymore. This is the computer's way of deleting something. It's just to update the stack pointer, just to behave as if there's no more return address part anymore, so that it deletes the contents. You may wonder, is the same piece of memory which was having the return address is still having the return address? The answer is yes. The piece of memory, even though the pointer no longer recognizes it, but this piece of memory is still holding the return address. The computer doesn't want to waste energy, and when delete something, it zeroes out all the contents. It's not necessary. So computer usually doesn't do that. It just leave it there. Just move the pointer, no longer recognize the space anymore. Then that space, even though it's holding data, is no longer recognizable, and the information is deleted equivalently well, right? But the data is still there. That's what I want to mention. That's also the reason why you accidentally delete something, delete your disk, and you bring your disk to some IT technician. They may be able to recover the data for you. It's just because of this. When you delete it, you just update your pointer to no longer recognize the data, but the data is still there. If the technician runs some programs, and then it could recover back, recognize the space, and then the data can come back. But that doesn't happen always. Sometimes when we delete, especially when you let's see, trading of your old phone, they would run a program that is zeroing out all the memory spaces and not to have such a potentially information leaking situation. So it's not always the case, but many of the cases, the data is still there. We have a similar situation when we update the stack pointer. Okay, back to our control transfer. So we update the stack pointer. So again, we update the stack pointer by adding 8. We are shrinking the stack again. And as a result, the pointer is moved up, and the outcome is we delete the return address. And this deal with the RET instruction. What happens next is the computer again look at the RIP instruction pointer and find out that the address of next instruction it's gonna execute is 400568. So it is the address right here. We're gonna execute this part. It shows us we jump back to the right location. We need to jump back to 400568 after the function call. By this way, we just have the callee to figure out what is the right return address to be, and have the callee change the instruction pointer to make that happen, and also we deleted the return address. So this is how the callee finds the way back to caller. Any questions? Okay, let's look at next slide. Data transfer. Data transfer talks about how the caller passes the inputs to the callee so that the callee can work on the inputs. For data transfer, we talk about we can also put this information on the stack so that the callee can check the stack to find out what is the input it is. And it is true for 32-bit machine. But for the 64-bit machine, right now we also introduce another 6 registers: RDI, RSI, RDX, RCX, R8, R9. 6 registers to hold the first 6 parameters as well. So we talk about the stack is set up to be the median for communication. We can use others as well. The registers could be one candidates. So for the 64-bit machine, or for past almost 1 decade, when we have the 64-bit machine, we use the 6 registers to help the stack to communicate, to facilitate the communicate. And when we have function call, we would have RDI, the registers, to carry the first parameter, RSI to carry the second parameter, RDX the third parameter, RCX the fourth, R8 the fifth, the R9 the sixth. So the first 6 parameters should go into RDI, and this should be set up by the caller. So caller get the control of the program, and the caller wants to pass the values to callee, and the caller just plays the first parameter in RDI, second parameter in RSI, so on and so on. If we could have more than 6 parameters, we could have 600 parameters if you like, and in such case, the extra parameters beyond 6 we can put down on the stack as a result. So that's why you see when the stack, we start from 7 until n, and the order matters as well. We would have first put the last argument n, and then push the next one n-1 into the argument 7. This is the order we push the parameters on the stack. We also have orders. So for the 64-bit machine, you can see the stack and the 6 registers are used as a median to let caller to tell callee what is the input values. And for callee, you can imagine when callee starts to execute its program, how about the callee wants to know what is the first parameter, then callee just go to RDI. This is a predetermined register which holds the first parameter. So callee knows this. Callee would go to RDI and find out what is the first parameter. If callee wants to see the 6th parameter, and then callee go to R9. And if Kali wants to know the seventh augment, and then Kali again go to the stack instead of the usual registers to find the seventh parameter. So that's how we have the caller and Kali use stack and the 6 param registers as a median to keep them on the same page of it. We talk about 32-bit machine and the 32-bit machine. The difference is we didn't use registers at all to pass parameters at the moment. So for 32-bit machine, we solely use the stack to pass all parameters, first, second, third, until n. We only use the stack to pass the parameters. This is the situation for a 32-bit machine. 64-bit machine, we have extra 6 registers to help us. This is about passing parameters from caller to Kali. Another part is about return value. For return value, we talk about how we can make the return. If Kali wants to return something, it just places the value inside RAX. This is the one and only one registers which is used to return a value. That's the only way, the only channel Kali can return a value to caller. You can imagine when caller finishes the function call, it wants to check what is the return value, and then caller can go to RAX and find out what is the value is, and then that's it. That's the only place we're gonna do that. That's why when you in C program, you can only return 1 variables. You cannot return, let's say, 3 or 4 variables. The reason is because of this. We just have 1 RAX, just have 8-byte RAX. That's the only place we can return. There's no way we can return 10 parameters, 10 variables at the same time because we don't have the space. But you may wonder if we have quite a large volume data, how we can return. In that case, you just return a pointer. You just return where this giant data is by returning the address of it, the pointer, to the caller. So the caller can have this address and find out the big volume of data. So you can either return a pointer or a single variable. The reason is just because of this. Our C they find out the assembly just have 1 registers to return value. So that's by default, you just use 1 variables, allow 1 variable to be returned. And this is how we make a return value. Any questions? Okay, let's continue to introduce. Here's the example. Here's the example we can pass parameters. If you look at the C program right here, we have a function called a pass. We have 8 parameters for this function, and we want to pass it to the Kali. What are we going to do? So you can see right now we are in the main function. In the main function, we need to prepare these values for the Kali. So first of all, we move number 1 into EDI. This is try to place the first parameter, which is 1, into EDI. Set it up. Then the color move 62 to ESI. This is ask2 code for the letter B. And then we move 3 into EDX. EDX is placed to receive the third parameter. And we also move 4 into RCX. Again, this is down by color. And fifth, we move number 5 to R8. Last, we move 6.1 to R9. This is ask2 code for letter A. Okay, we use up 6 registers to pass the first 6 parameters. And then we have more. We have 7 and 8. What are we gonna do? We just put that on the stack. Put that on the stack. 8 is here. We make the function call. And then we make the function call. This is what has been done by color, and the path give the values to different locations. And you can imagine if you are the colleague, you get a chance to execute your codes, and you want to look at the parameters. You can go to different registers or on the stacks to find the values you need. This is a way we can find it out. Okay, so we will save this for next lecture. Let's first look at local variables on the stack. In the previous case, the stack, we generalize the stack as a median for the color and collie to be on the same page. Now the stack we will introduce, actually it plays more roles than that. If we have local variables, we put that local variables on our stack. Here's the example. We have function func, and we have 4 local variables initiated. And let's look at where this local variable is. Set it up. Okay, you can see we move number 1 to RBP -4. So RBP is a base pointer. So we talk about stack pointer. Stack pointer points to the top of the stack. RBP is a base pointer. Base pointer is pointing to the bottom of the stack. So if we have a stack, let's see, this is stack. Here's the bottom. And we have the RBP, base pointer, points to the bottom of it. Let's see, here's the top. Then we have RSP to points to the top of it. So this a pairs of pointers is just trying to tell us where stack is. We not only can look at its bottom, but I can also look at its top by using RBP or RSP. And when we have 4 local variables, we just place that on the stack. The first one, the integer 1, we just place on the stack. And then the second one is number 2. We find a place to give it to 2. And we can also have ask2 code for number 1, and then 31. 31 is the ask2 code. And also finally, we have a long variable occupying 8 bytes, and then we give that on the stack. So you can see that is on the stack. And here I will talk about one idea. When you learn C program, you when you set up local variables, it only makes sense to your function. Let's see. Here we have variable A, B, C, D, right? This A, B, C, D, these four variables only make sense to func. If we have another function, main function, does main function can recognize A, B, C, D? My question is, does main function can recognize A, B, C, D?
Nope.
Yeah. Sorry, I didn't hear. Is there any volunteer? Could I ask, answer this question? Yeah, thank you, Devin and Marcus. Yeah, no. Main function cannot recognize ABCD because ABCD are local variable, only visible to the function func. Could you guess why? Any clue why local variable only makes sense to func, not to other functions?
It's because as soon as the function is done, it pops off the function call stack, and then everything that was there is the data is still there, but it's no longer recognizable by the pointers.
Yeah, that's right. Thank you, Isaac. That's a good answer. The reason we no longer the reason that the local variable only makes sense to func is when we finish func. Do you remember the process? Let's see, right now, this is stack pointer. When we finish this, we need to move stack pointer back to shrink our stack because we no longer need it. In the previous case, let me show you. Oh, it's long ago. Anyway, so we need to delete something because it's no longer usable for us. We need to go back. And the stuff we delete is not only return address in our previous example, but also all these local variables stored on the stack. So right now, let's see, we move back from here, and then the pointer can no longer recognize the space here. It just treats this space to be empty. And then, how come other functions could recognize ABCD? Because the space is already gone. Nobody can recognize ABCD anymore. That's the reason the local variable only makes sense to the func in our case. It's just because after function call, we just delete these local variables along with the return addresses, and then we no longer have space for them. And when we do other functions have no idea about it at all. That's the reason. Okay. Great. Do you have other questions? Okay, let's continue. Local variables, we can place that on our stack, but because we delete the whole stuff after function call, so it's only makes sense to the func, not to other functions. And here we talk about another issue, which comes from sharing registers. We talk about 16 registers. For these 16 registers, they are shared by caller and callee. So you can imagine there could be some conflicting situation. 16 registers. We only have 16, and they shared by caller and callee at the same time. And this could be an issue. Let's see, caller is using RDI. Let's say this register caller wants to use, and maybe caller put down number 5 inside of it, RDI. Then caller makes function call. Callee gets the control of the program, and now let's say callee don't know anything about it. Callee just want to make RDI to be 10. Callee makes it to be 10. And then how about after function call return? What would be the problem? The caller's register is messed up, right? Caller have the original value 5, and then caller just make a function call, and then callee just move 10 into RDI, and the callee return, and then caller go to RDI and find that the value right now is 10 instead of 5. So it has been messed up by callee, right? This is an example of confliction if we share resources. Is that clear? Yeah, when we share resources, then that could be the confliction we have. And then we need some rules, some mechanisms that a caller and a callee can agree upon and try to reduce such confliction as much as possible. That comes to the idea of callee save the registers and the caller save the registers. Let's take this RDI, still RDI as an example. What it means callee saved register? The callee saved register is it's callee's job to it's caller's priority over using a register. Let's just assume RDI caller have the priority over using it. What could be the outcome if the caller claims priority over RDI? That means if callee wants to use RDI, it has to save RDI at first. Save this number 5 at first. And then callee just use RDI as much as it wants, right? It can freely use RDI. But when callee trying to return, it has to restore the original value of RDI. It's callee's job to restore. In our case, that is to put number 5 back into RDI before makes function call return. That's callee's job. The reason is caller claims priority over RDI. So if callee wants to use, it's callee's job to keep the original value to be the same before make return. That's the way. Save the value, and use RDI as much as it wants, and then finally restore RDI value before make return. That's the way we can make it out. This process is called the callee save register. Okay, is that clear? Okay, good. Now let's look at another case, color saved register. If we talk about color saved register, we are assuming equal rights over using RDI. Let's just assume RDI is color saved registers. We have equal rights. Color and Kali, they are equal. So the Kali doesn't have to do that anymore. We're equal, right? but a color that brings some headache to color. Color used as 5, and a Kali change that to be 10, and a Kali return. And then color find the RDI is 10 instead of 5. And a color cannot complain. Color cannot complain because they are equal. There's no way Kali has to do a favor for color. No such a thing. So the color face such an issue. What a color can do? Okay, color can do something. Color can save RDI. This is what a color do. Save RDI. Save this number 5. Okay, it makes function call, and a Kali can do whatever Kali wants to do over RDI, and a Kali return. Kali return and a color before using RDI. That could be possible. RDI has been used by Kali and messed up by Kali. What a color can do? Color restores RDI by itself and move this number 5 back to RDI again, right? Its color does this. It restores RDI by itself. So we call this color saved registers. That's the 2 ways we can solve this dilemma. We either have Kali saved registers. In such a case, the color have priority over the registers, or we can use color saved registers. That is color's job to save the value, to restore it after function call, if the color wants to see the same value inside of the register. So that's the way we can do it. And which registers is Kali, which one is color saved registers? That is predetermined. Let me give you some example. RBP, base pointer, this is Kali saved register. Same RSP, this is all Kali saved registers. And in other registers, many other registers, like let's see, RDX or whatever, these normal registers, they could be color saved registers. Okay, that's how we have 2 mechanisms to deal with the conflicting usage of the common registers. That's 2 ways we can do over it. So we almost 4:20. So that will be our today's comment. If you have any questions, you can ask. I will be around. Yeah, thank you for attending.
I have a quick question.
Yeah, go ahead.